Okay, then we are going to share the screen. Share screen. Okay. I think I have already posted the study guide on our course website. And for the final exam, the study guide, and I remember I also posted the solution. So you can also take a look over the solution. And over here, I'm just quickly go over the solution. So regarding the programming parts, so the major concentration for our final exam is you need to know how to use linked list. Okay, how to use a linked list to do something. So you need to, and I'm not going to ask you to implement the linked way of linked list. So if you know, hold on, let me add those two students. So what in our final exam you need to know is you need to be familiar with the collection frameworks linked list. Okay, so like over here, so you need to get familiar. And previously we discussed quite a lot about the collection framework. So, and we will focus on linked list. So you just get familiar with the linked. I remember on our study guide section, I also posted a Oracle official documentation regarding linked list. So you can also review that part to get familiar with all of its methods, functions within the linked list. Okay, so over here, what I ask you to do is you need to design a class. And this class needed to be a generic class, okay, generic class, and we call it DAC-G in this case. So any name, is it? And it's a generic one. So we have this diamond, the pair of diamond, is it? But over here, because we are going to, so you can check the required method. If the required method involved any comparison, is it? Then generally speaking, you also recommend your generic extend to support the comparable interface. Okay, so that's why we do here. So this DAC-G class is a generic class, and it also supports the comparable, okay? And because we are going to use the linked list, is it? So in this case, we only have this single instance method for this class DAC-G, and the type of this instance variable is called linked list, okay? So this is from collection frameworks linked list. And I also initialize this linked list. Okay, you need to call new linked list, is it? You need to initialize it. And then within this class, I ask you to write a couple of functions, is it? And one of the methods I ask you to check if this instance variable, okay, is arranged in ascending order. So I ask you to check if it is in ascending order, is it? So we have some cases to discuss. Is it, of course, if your linked list, if you only have one item in your linked list, then by default, we just said, okay, it should return true, okay? And then the second part, then you need to find out, because this is a linked list, is it? So you want to know, okay, 100, like suppose here's 300, and then here's 200. Then you know this is not in ascending order. Is it? How do we find it? So we are going to do the loop, is it? But over here, because we are going to compare the current item, so that's indexed by I. And how do you find like 100, 300, or 200 that in linked list? There is a function method called get function, and you pass in the index, then you can get that item, okay? And with this get I, and you want to compare with its next item, one by one, so that's why, because you're going to compare with the next item, so that's why I'm not going to loop all the way to the last item. I'm going to loop the one before the last item so that you can still check, do the comparison with the last item, and over here you need to call that compare to, because this is generic, suppose it's not just primitive, so you need to call the compare to, okay? And if it's always like meet your ascending order, then you can move forward, If this is not the case, then you say, okay, I'm just return false, If you complete your loop, then of course you can return true. That means every comparison meet the conditions that you defined. So you can see it's quite a simple one, a method. But the key point over here is you need to get familiar with this linked list data structure. Okay, you need to get familiar with all of the methods. In this case, okay, we know, okay, it has size function, it has get function, So all of those you need to kind of get familiar. And then what the next one shows. So the next one want you to return part of your linked list and indicate, also let you return how many items in part of that linked list. So the idea is, okay, I have a linked list. Suppose I want to return the first three, as also the partial list, linked list. So how do I do that? So then in this case, the return type, of course, need to be that linked list, Because the return type is a linked list, so that's why over here, okay, you need to, because you're going to return a linked list, so you need to have a variable, to hold the linked list so that you can return, okay? And the same thing, you can also initialize it, And of course, if n is greater than the total size, the length of the linked list, so over here we just said, okay, we don't return anything, okay? Otherwise, if it's part of the linked list, if it's less than, then you can start to get from that specific index number, and all the way to the end of the linked list. And you get, we call the get item again, and you're going to add the item to that newly linked list that you're going to return. So this time we call the add method, and then you just return that partial linked list. But over here, for this case, this is not a real deep copy of the linked list. So this linked list of the item is going to return, it's going to refer the items within the M linked list. Okay, so it's not a completely a deep copy of that. And if you really want to have a completely independent linked list, then you need to also find a way to copy each node's contents to this return linked list. And it's with the generic version, it's quite comprehensive here, okay? And if you want to just do clonable, that won't work. Okay, that I just clone part of the linked list. Previously, we investigated, is it for data structure? If you just do the clone, that's just a shallow copy, not a deep copy. Okay, and if you do want, then it's kind of you need to whatever this get return, that's an object, is it? That need to support the real clone, is it? But for generic, that's hard to achieve. Okay, how do you make a generic to also support the deep copy? Okay, so that's very hard to achieve also. So generally speaking, so if you hear just one call clone, that won't work. If you said here, I just call clone, that won't work. Okay, it's not going to work. It's not going to work because there is no definition. Okay, so how do we really achieve the deep copy for each of the item? Okay, so that's a that's some other story. And if you do want, and some author recommend you can do like this, and you can get some the type of this. Is it you can call like some get class? Is it? And then you call that then call some clone. Is it call some method called get method, and within the get method you can plug in clone. Okay, and plus something, and you can check after class if you're interested. You can call get clone or get method and plug in with the clone method. But there is an issue with this, okay, because this is kind of you get to. So if your code support this, then there's some security issue, okay, because this kind of gave some whatever you define the generic object that E here, kind of some privilege. That privilege can go to, you see, can go to some of its object's own settings, configurations. And generally speaking, you don't want that to be happened, okay? So that's not a recommendation. And there's some other recommendation is you can do some serialization. Okay, to do the real deep copy one, but that's already beyond our class. Okay, that's very advanced Java discussion. Okay, so anyway, so here, what we can do is can only do a shallow copy one. Okay. So that's regarding this get partial list. But over here, what we are interested is how do we loop, how do we add, okay? And what the next one shows is we need to check if two linked list has some same item, okay? So over here, we have two linked list. We have the M list, is it? So M list, so you have 100, 200, something is it? So this linked list, this is M list, is it? And what you are going to do is, it involves a second list. It's called parameter list. Is it? It's maybe 101, 201. Is it maybe have 300? Is it something like that? Is it over here? This so. This two has one same item. So this linked list is a parameter list. That's it. So what I ask you to do is you compare these two linked lists to see if they at least have a single item that's the same. Okay. So that's the idea. So how do we do this? And of course, you need a loop, is it? And in this case, we have the outer loop. So the outer loop loops through the M list, looks the object itself, the instance variable, is it? So it's start from 100, is it? So from 100, then you're going to compare with every single of the item from the M list, is it? So that's why then you have the inner loop, is it? And you're going to compare with every single one of it, is it? And over here we use the for each loop, is it? Because that's a collection and it's support for each loop. And over here we call the compare to, okay, for the comparison, is it? Because you don't, because this is supposed to be very generic, is it? If you call the compare to it, just compare if those two have the same contents, okay? And if you find it, is it? Then you just return, is it? So over here you break out the loop, is it? Otherwise, then it's going to move to 200, is it? And then 200 will compare with every single item within the linked list. And then 300 is a compare. So it's just keep doing like this. Is it? So that's why over here you need two level of loop. You need an outer loop, is it? And outer loop is a loop through the list. And you also need an inner loop. Inner loop loops through the other list. Okay, so that's the idea over here. And here I said, do you want to do like the contain, is it? And it's not recommended to use contain because contain only works for shallow copy. Okay, so that's why over here we try to avoid, because this is a generic. You want it to support as more possibility as better, is it? If it can support deeper copy. So that's why over here we try to avoid to use that contain, okay? And then the next function over here is I just call push second, is it? To add as a second item. How do you do it? Is it? It's pretty straightforward. For linked list, you have a multiple add method, so you can choose. And this add method just add at the back. Is it? Over here, you can also specify where you're going to add. Is it? And the last one is just a regular toString function. Okay, just output all of the contents of this linked list. And what I did here with this application, I try to show how it can support some class that you define yourself. Is it like the book class? And this book class also implement a comparable. Is it comparable? And this then will work with our DAC. Is it? Because the DAX E, it must be what? Extend comparable. Is it? So our book class meet that definition. Is it? And I also gave the compare to method. And then in main driver, we try to test it. We try with our book, is it? And we add a bunch of book, is it? And then you can check if this DAC G is arranged as ascending order, is it? We can check it. And we can also check the get partial list, is it? But here I try to also show you over here, this is a shallow copy. Okay, after you get this partial list, is it? And I try to get one of the item, is it? Get that item, and I will get from the third, is it? Beyond the third of the remaining list, is it? That's AR2. And then with that, I'm trying to change it, is it? ID and the name, is it? For the book. And then you will see. And over here, I try to output what? I try to output the original linked list. You will think that your set is only done on AR22, is it? But you will see this guy also got modified. Is it? That's why I said what we just did is a shallow copy, okay? And let's see. And what is the next part? Just try to show, okay, I create another linked list, AR2. Is it? This is its own version, is it? Then you are going to check if AR and AR2, is it, are the same, is it? AR is what? AR is a DAC, is it DAC G class that you define, is it? And you want to check if that data structure has some same item with this linked list. Is it with this linked list? So how do we check? Is it we can call that has same item that we just defined, okay? And then we can run it and to take a look at the result. You can find it. I said it's not in ascending order. It's very obvious, is it? And also the partial list, is it? You will see that did get modified. So it's a shallow copy, okay? And the last part has the same item. Yeah, it does find one of, at least one of the same items. So, okay, so that's regarding the final exam review. So you can go ahead and check our study guide. That's a major information. And what next we are going to do is we are going to start with a new topic, okay? Okay, so what we are going to study today is the introduction of tree structure, because so far what we learned is kind of linear, is it? So it's in a line kind of data structure. Is it? Now it's tree kind of data structure, and this is the starting point. We call it a binary search tree. And it's mostly used for search, okay? Binary search tree. And it has some special arrangement, okay? So, and you also see this abbreviation at BST, okay? Binary search tree, okay? And we learned, and we will discuss the implementation, also linked implementation. Linked implementation. So kind of like what we previously discussed as a linked list, is it? For linked list, the basic building unit is what? Is a node, is it? A node. A node has two parts, is it? The data parts, is it? And another thing we call it a pointer to the next node, is it? And the type is the node itself, is it? So then you can chain them together, is it? To build as a linked data structure, is it? Linked, and it's also linear linked data structure. Okay, and what over here is because it's a tree, and here it says a binary tree. Okay, binary tree means only two branches, is it? And what that's going to look like? So it's kind of look like this. It's a binary tree. Is this something looks like this? Is it? So each, and over here we have the node. Okay, so those are called nodes. Okay, and so each node it's going to have two outgoing arch, kind of, is it? And compare with the node in linked list, it only has one outgoing arch, is it? And over here we have two. Okay, so later on we will see if we want to implement, then in this case we need a node. We call it a bin node. So basically binary node. Okay, a binary node, it has also needed to have some data, is it? But this time it needs two arc to going out, is it? And one we call it left, and the other we call it right. Okay, so it has its left child, we call it left child or right child, is it? Okay, so that's the general idea. So next, let's see an example, okay, what a binary search tree looks like. Suppose I have a sequence of numbers. I have 55, okay, 50, 38, and 51, 39, and then 60, 57, 65, 59. And I have this sequence of number, is it? And you can store this sequence number in any kind of data structure, is it? And over here, I wanted to store them. So store them in a binary search tree. Okay, so what does that mean? Okay, and so you have this sequence of number. The first number you get is 55. Okay, so what I will have 55. Put it here. Okay, that's the first node I'm going to create. And then you move to the next number. The next number is 50. When you have 50, because you're going to arrange it in a binary search tree, as it store them in a tree. Okay, not in an array, not in an array list, not in a linked list, not a stack, not a queue, not a DAC. Okay, not any of that so far we have learned that it's in a tree. How do you store them in a tree? Okay, so we have 50, so it has some special rule, is it? So you have 50, then you compare with 55. If it's less than 55, is it? And then you let it store in the left part. Okay, left part. And then you move to the next 38. Okay, I have 38. So you always start from the first one. As you compare with 55, it's less than. So you know that it should go to the left. Okay, go to the left, then it's 50. You compare with it, it's less than. So you know you need to get it to the left. So you create another node and you store it to the left of 50. Okay, to the left branch of 50. Okay, 38. And then we have 51. Is it? At 51, same thing. You start with 55. You compare it's less, so you know you're going to go to the left part branch. And you move to 50. You compare with 50, it's what? It's greater than 50, is it? So it should go to the right branch to be stored. So it's stored as 51. And next is 39. And same thing, you start from the top. It's less than, go to the left, compare with 50, it's less. And then you compare with 38. It's greater, is it? So that's why you need to store it to the right, okay, to the right. And then you move to 60. Okay, same thing, start from the very top, is it? It's greater than, so it should go to the right part. Okay, so you have a node created and you store it here. Okay, 60. And then what? 57. Same thing, you compare with 55. It's greater than 55, so it should go to right. And then compare with 60, it's less than 60, so it should go to left. Okay, and then nothing here, so that's why you create and you store it. Then next is 65. So same thing, 55 greater, compare with 60 greater, and there is no, it needs to go to right, but there is nothing on the right. So then you can create the node and store it here, 65. And then next 59, start from the beginning. Is it 55 compare? And then it's greater, so you along the right subtree. And compare with 60, it's less than, so you should go to left, is it? And then you reach 57. You compare with 57, it's greater, so it should go to right. And there is nothing to the right, so you create that node and you store it in this node. And now you finish, store everything in the tree. So you create this tree and you store it. Is it? You store it. And this, so this graph that we just draw, this graph that we just draw, this is called a binary search tree. Binary search tree. Okay, binary search. And within this tree, we have some terms. This very top one, the first one that you stored, is it? And this, we call it a root node. Same thing as linked list, okay? Each of the item is going to be stored in a node, okay? So the very top one, the very first one, so basically the first item you create in the tree is called a root node, okay, root node. And then over here, so after, from this root node, you have two branch, then you have two branch, is it? And if you take a look, you will find this whole thing. Is it what I just dot circle part? This is a tree itself. It's also a tree. And this kind of tree, we call it a subtree. Subtree. Is it a subtree? And this subtree is on the left part of the root node. Is it? So we call it left subtree. Okay, and the other part, like this is the right subtree. Okay, and basically you will also see, like even regarding node 50, is it? It also has its left subtree and right subtree, is it? So left subtree and right subtree. Is it? So it's a kind of a recursive idea, is it? So each node, because each node can have two subtrees, is it left subtree and right subtree? Okay, so that's a term. And also, let's see, we also call generally in regarding graph, okay, we call the item is enclosed, we call it a node. Okay, we call it a node, okay. And this kind of a line, is it? We call it an edge. An edge, okay. And also there is a relationship between the nodes. Is it 60 versus 65 and 55 versus 60? Is it? Generally speaking, we say, okay, 55 is a parent node of node 60, okay. So this is considered as parent node. Okay, same thing like over here, the 57 is also parent node of node 59, is it? And the node 59, then it's a child node of node 57. Okay, so this is regarding the relationship between two nodes, okay, parent and child relationship. So if there is an arc, is it going toward the node, is it? Then that node is a child node. And if the arc coming out of that arc, then that node consider the child node is a parent node, okay. And there is some other concept within this whole tree structure. If you take another close look, some special node, 39, 51, 59, 65, all these four nodes, is it? You will see there is no outgoing arcs, is it? So this kind of node, we call them what? A leaf node. It's like in a tree, is it? There is no branch anymore, is it? So the node, we give it a definition called a leaf node, okay. So this is a general term regarding the tree, is it? And for the root node, you can also see, root node, there is no incoming, is it? Arc, no incoming arcs, is it? That's the definition for root node, okay? So we have root node, we have leaf node, is it? And some other nodes, and the parent node and the child node, the relationship, okay? So for a root node, then in this case, it has two subtrees, the left subtree and the right subtree. And I'm not sure if you see any patterns regarding the left subtree and the right subtree versus node 55. I'm not sure if you see any let's see. Okay, if I can get this. If you see any features here. If you see any features, and if you take a close look, you will. Did you find that? Draw. Did you see that all of the left 50, 51, 39, 70, 38, they are all less than 55? Is it? So a node's the left subtree, all of the contents is going to be what? Less than the node's contents. And the right subtree part, if you compare, is it? They are all greater than 55. Is it greater than 55? So that's the feature, is it? So it has a special feature, okay. And then the idea is, why do we need a binary search tree? Is it because once you have a binary search tree, not like a binary search, as previously we learned that binary search compare with linear search, it's faster, is it? Because you only need log 2n kind of comparison, is it? Even that's a worst case scenario, is it? Average case of scenario. And for the binary search tree, and there is no precondition, not like a binary search. Binary search of the items needed to be arranged in ascending order, is it, or descending order, so that you can apply binary search. A binary search tree, there is no such requirement, is it? You can, so the sequence of item coming into when you build the tree, it doesn't have specific order that you need to follow, is it? And then you're just going to build the tree to store all the items. But still we can see, suppose over here I said, oh, can you tell me if 39 is in this tree, is it? Or let's see, 59. Is it? Suppose I want you to tell me if 59 is in this sequence of time. How do we do that? And based on the feature that we just discussed, is it once you build the tree, is it? Then it's going to be, let's see, how do we find it? It's a search, is it? Okay, so 59, then you want to search the tree, is it? So you're going to start with the root node. Is it because you have the tree? I'm going to start with the root node. And I compare 59 with 55. As it's greater than 55. If it's greater than 55, then you know you don't need to worry its left subtree anymore. It's definitely going to be in the right subtree, is it? So I'm just going to follow its right branch, reach the next node, is it? When I reach the next one, I compare with 60. Oh, it's less than 60. Is it? So I know I don't need to worry the right subtree. I can compare through it. I just need to follow the left subtree. Is it? Follow the left subtree, then you see you find it. Is it? So how many comparison? You just compare 1, 2, 3. You just have 3 comparison. Is it? Comparison. Versus, because this item is at the very end of the list, is it? compare with a linear one, then you need to start with one by one comparison. Is it how many comparisons you need to? 1, 2, 3, 4, 5, 6, 7, 8, 9. You need 9 comparisons. Is it? So this is much faster. Is it? So that's why we think it's much more efficient, okay, if you store items in binary search tree. And this is just some small thing that if you have a huge tree, just think about how efficient it is it? So that's regarding the binary search tree, the basic concept, okay. And the next, let's take a look, how do we build the binary search tree? Is that we have the concept here. So the binary search tree search concept, we already kind of understand it. So suppose, let's see. Let's draw another tree to see if we can do. Yeah, suppose we have this tree. Okay, we have this 55, and then we have 50, and then we have 60 here, and we have 38. And we have 51 here. Suppose the tree is already exist. Okay. And then 65, is it? So with assuming the tree already built, the next class we are going to discuss how do we build the tree. And we are going to do search. You try to find some item, is it? In this case, how about, let's see, okay, suppose we try to find 51, is it? So the way to do it is start at root. Start at root, is it? And then you compare, is it? Compare, is it? And compare, and if less than root information, you do what? You go left branch. Is it? Go to left branch. So I find 50. Is it? By 50, then you're going to keep doing like this. Is it? Then compare again. Is it? And it's greater, is it? And if greater than the node item, is it? Then you go to right. Is it? Go right. Is it? And then you compare the next node, is it? And you find both are the same, is it? Then you say, okay, this is the item that I found, is it? And suppose you want to find some other time, 90. Is it? 90, you go from the root, is it? Start with root. It's greater, so I'm going to go to right. And it's greater than 60, so I'm going to go to the right. And it's greater than 65, but there is nothing, is it? So it's null, is it? So you already reached null, so that means, so if null, is it? If null, that means the item not in the tree. Is it? Not in the tree? Okay, so this is the general idea about how to do the search. Okay, so today I'm going to give you some concept of how to do some insert and delete, insert search thing. Then next time, tomorrow we can go ahead discuss about coding. So next is about insert. Okay, so basically it's how do we build a tree. Okay, build a tree. So this time, let's see, we have sequence of characters. Suppose I have O, E, T, C, M, P, U. Is it? I have this sequence of items, so I'm going to build the tree. So I have O here, is it? And then I have E here, is it? And then I have T here, and then I have C here, and I have M here, and I have P here, Z, and I have U here. Okay, and also another concept is if you take a look, you will find this tree it has a similar kind of number of nodes on its left and right subtree, and also the level of the left and right subtree, the depths kind of the same, is it? So this is considered as a balanced tree. Okay, balanced tree. So now let's see, I want you to insert R, letter R. Okay, so where should I put in this tree? Is it? So when you do insert, basically you start with search, is it? And also another concept here is with BST. So each node is unique. Is unique. Okay, it doesn't allow duplicate item to be stored in a tree. Okay, so each node has only the item that occurred only once. So then let's see R. Okay, so we go with the start with the root node. You compare, so it's greater than O. So we need to go to its right. Is it? Then you compare with R. It's less than, so it should go to the left tree. Is it? And now you reach a P. As it compare with P, it should be greater than, so it's supposed to go to right. Is it? But P doesn't have, P is already a leaf node. Is it? A leaf node. So there is no branch for you to go. Is it? So what should I do is, then you need to create this node. So create a node. Basically, in this case, it's going to be a bin node. Is it? And then what? You let node P. So node P is going to be the parent node regarding this new node you create. Is it? And let this parent node's left branch, is it, point to this node. Then in this case, you get R inserted into the tree. Is it? And suppose you want to insert M, then you cannot do it because you find M is here. Is it? M is already in the tree. Then no more insertion. Okay, so be careful about this concept. Okay, so this is the concept of how to how to add item in the tree. And the next, let's see another concept about the traversing. Okay, so let's take another look at the tree. Suppose we have a tree look like this. We have letter G, and then we have letter F on the left, and we have node J on the right. Okay, and then we have node A on the left, and node E on the right. And then over here, I have node H, and I have node O. Okay, I have this tree, is it? So tree is here. So you remember previously we learned in linked list, is it? We learned traversal, is it? Traversal is node by node visit, is it? And in tree, it's not linear, so how do we do the traversing, is it? And so far, we already see, no matter search or you do insert, the only way you can start is from where? Is always start from root node. Is it a root node? Okay, so then for traversing, how do we do it? Is it? So there are a couple of ways we can do traversing. The first, we call it in order traversing. Traversal. Okay, in order traversal, the general order is, we call it L, then N, then R. Okay, so what does that mean? That means you go to left first. Okay, go to left first, and then go back to node, and then go to right. Okay, then go to right. So let's see how this is going to work. Okay, so you start from the root node. Okay, start from root node, and then you go to the left. You're not going to stop here because it has branch left. You go to left, and you're supposed to go to the left, is it? But there is no left in this case, is it? So you stop, is it? So the left part you finish. Okay, you finish. And then you move to node, is it? Okay, I do have node here, A, is it? That's why I output A. I output A, okay? And then what? Then you need to go to right. Okay, what to write is? It's E. So I'm going to output E. Okay, so now regarding you need to go back, is it? So this whole left branch finish, is it? So regarding node F, you are done with the left, is it? So the next step is what? You need to do node. So node is F, so I output F, is it? And after you finish, you should go to right. Right is no, is it? So nothing here, is it? So now you finish this whole section, is it? This whole section regarding root node is what? Is a left tree, is it? So still follow this, is it? You finish left, then I need to come back to node, is it? Node is G. Okay, G I finish. And then I go to right, is it? I go to right. But you go to right, here is your node, is it? Okay, because you always need to follow what? L, left, node, and right. Is that you always need to follow that order as they're traversing. Okay, so you cannot stop here. Is that you need to go to left. Is that okay? The left is what? What is it? This is H. Is it H? And the H, and then you are supposed to go to its left. Is it? There is nothing left. Is it? So you go back to what? No. Is it? So that's why you output H. And then you're supposed to go to right. Is it? But there is nothing for right. Is it? So you are done with left again. Is it? So left you are done. And then I need to move to node. Is it? To node. Node is what? Node is J. Is it? So I finish it with J. Is it? I need to move to right. Is it? The right is what? Okay, right is O. Is it? So I'm done with the right also. Now I'm also done with regarding the node, the whole right branch. Is it? So the traversing, the in order traversing, you will see the output is going to be what? It's kind of like arranged in what? In ascending order. Is it? Ascending order. Is it? So that's going to be the output, ascending order. Okay. So how do we get the whole traversing work in coding? So that will be tomorrow's material. So basically, we are done today. I think already past the time. And do you have any questions? No question? If you want, you can send your name to the chat so I can keep track and later on add the bonus points.